Okay, let's see everyone here. Let me grab my charger. So today is the last lecture on data structures. And from next week, it will start getting a bit more interesting and hopefully a bit more fun, because we are going to actually start working with actual websites with HTML and CSS and JavaScript all together. And so that's also always a bit fun, because at least you can see some things in like a website and you feel like you're creating something. And even if it's just a hello world text, then it always feels better. Some of these things that we have done till now feel a bit theoretical, but they are going to be used for sure, because at the end, when we practice JavaScript, we will be using JavaScript as well with the websites. And in order to do more complex things, we will also need to use more complex functions. And that may mean, for example, recursion as well, even if it's not recursion on trees or on linked lists. But we will for sure see many of the things that we have tried so far. Okay, so let me share my screen and try to go over graphs. Okay, so graphs, we will see today what is a graph data structure and what it is useful, what is it useful for, how do you add, update, retrieve, and delete values in a graph, same as we have done with trees, and how do you do depth first and breadth first sets. Similar to what we have seen in trees, we can do also in graphs. Because graphs, it's a similar structure to data to trees. Here it says graphs are everywhere, and the example it uses is of a chip that they have some connections, and these connections can be represented as a graph. I don't think it's the best example, because in fact, graphs can be used in so many more places that we actually have more contact with than a chip, than some electronics. So for example, a map, it's a very common use of graphs, because at the end, cities or places can be considered as nodes that are connected between them by roads. And Google Maps or any kind of map is using graphs. Also, a social network, any kind of network, basically in computer networks, the internet is a big graph where all computers are connected between them. So we have the nodes, and then we have the connections, the line connections. Or a social network, we have us connected to some friends, and then the friends connected to some other friends, and all this creates a big network, and any network can be represented by a graph. So yes, graphs are everywhere in computer science, and they are very useful. And especially if you are going to work like this with networks or something that has to do with networks, a graph structure will probably come up. And there is also a common problem, that the traveling salesman problem, that it's a very famous graph problem. Given a list of cities and the distance between each pair of cities, what is the shortest way, the shortest route of going from one to the other? So this is also a very typical computer science problem that may come up maybe in some interview, that you have some kind of graph, you have cities connected between them, and you want to know what is the shortest way of going from one place to the other. This is called the traveling salesman, because it's supposed to be a salesman that, in order to optimize its time and its effort and energy, will try to visit all cities in the shortest amount of time. Okay, so graphs are everywhere, and this is a graph. And let's go again over some vocabulary, same as we did with trees. It's a bit different than the trees. So we have these nodes. All these are nodes. And we can also find them with the word vertex. And then we have links between the nodes. So this link can also be called an edge that connects nodes. Not all nodes have to be connected with all other nodes. So there are graphs where everyone is connected with everyone else, and these are the fully connected graphs. But there can be graphs where they are not. And so a tree, for example, it's a form of graph, but there are not all connections there. So in this case, we don't have a parent-child relationship as we had with the trees, because in a graph, every node can be a root. So in a graph, we don't have any concrete root. 4 can be a root, 5 can be considered a root, 3 can be considered a root. So every node, it depends on where we want to start our search from, and this can be a root. And so instead of parent and child and siblings, we have adjacent nodes. So it's just the neighbors that we see. So 1 has 5 and 2 as adjacent nodes, as neighbors. And then 5 has 1, 2, and 4 as its adjacent nodes. But there is no parent-child relationship here. And we can also have directed or undirected graph. So if we can go in these links only one direction, so only from 1 to 5, so if it was some kind of an arrow, imagine, then this would be a directed graph. If both ways are connected, so we could go also the other way, then this is an undirected graph. In here, we will work with undirected, so we will not take any care of direction. And also, there can be some value on the edge, on the link here. So maybe between 5 and 4, there is a value of a weight, as we say, of 10. That means, for example, how much is the distance between 5 and 4? In example, the one that I showed you with a traveling salesman, we will need some kind of measure of how much is the distance between these two cities, and this will be the weight of this link. That we could also consider. But again, here for our examples, we will not consider any weight for the links. And so there are a lot of ways to store a graph. This is not the only way. We will use this way for that we do today. So how we will store it? We will create a graph class, and then it will have this .nodes object. We're not going to create each node individually as we did with linked list. So we're not going to have a node class and then a graph class that we will use the node class. No, we're not going to have two classes. We're not going to have a node class. It's going to be just one class, the graph class, and then we will have just one object to store everything. And the representation will be like this. So an object where each node will be the key of the property, and then the value will be an array of the adjacent nodes. Okay, so this graph can be represented with this object. Node 1 has 2 and 5 in its array as its adjacent nodes, and then 2 has 1, 5, and 3, 1, 3, and 5. We can store it numerically if you want, as its adjacent nodes. 3 has 2 and 4, and so on. And since we are working with bidirectional graph, so there is no only one way, so both ways can go. So both vertices, both nodes must contain reference to the adjacent nodes. So 1 contains reference to 5, and also 5 contains reference to 1. Okay, so questions on this, because we will use this for the activity. So if this representation is clear on how we represent this graph with an object. So let's see another example. If I have this graph here, and I want to transform this to an object, you can see my screen, right? This, okay. So so how will I write this object? Let's say let node equal, and I have a big object. In fact, I will do this as code. So how would you write it? Suggestions. You can start from anywhere, right? You don't have a concrete starting point. There is no root, so you can start from any node you want and like add nodes to my graph, to this nodes object.
I will start with A.
So A would be one of the keys of the object.
And
then
it will have
yes.
D, B, D, and E.
B, D, and E. Okay, then
B will have A and C.
A and C, yes, correct.
And
So
then
depends.
C will have,
yes. So I mean,
yeah,
then it depends on how
it's
you
for
want
me
to,
like easier to think.
To go like this, if you want to take the the letters like in order, or if you would like to do, for example, like since I have created A and it has B, D, and E, then I will first finish the neighbors of A. So these are a bit the difference also between breadth first and depth first. So maybe here you have added A and it has these three neighbors, and then maybe you want to add B and then go with D and then go with E before you continue with maybe C, which is the neighbor of B, etc. But this we will see how it's done, the traversal. But the idea is as you are saying. So then D will have also an array, E and E, and so on. Okay, and this will be our graph representation. Okay, so we will create this class, the graph class, and the constructor will just have this nodes object inside. At the beginning, it will be empty. And then every time we want to add a node, then we just add the node with at the beginning an empty array, and then we fill the array with the neighbors. So I'm going to, let's say I have these nodes already added, 1, 2, and 3 are already added with the neighbors, the adjacent nodes already created in here. And then I want to add node 4. That means that I'm adding a property 4 to this nodes object at the beginning with an empty array. And then I need to update the array of 4 with its neighbors, so 1, but also update the array of 1 to include 4 now. Okay, because remember that it works both ways, so the relationship has to be in both arrays. So I don't only need to write this new node with its own neighbors, but also update the other neighbors as well. So 1 is a neighbor of 4, so it will also have 4 in its array. And we will see it in code in a moment. So compared to trees, there are some differences. And the main difference is that on a tree, we can never have a loop. We can never have a circle. And in a graph, we can. So in a tree, any two vertices, any two nodes, they are connected by exactly one path. In order to go from H to F, I can only go, oops, I didn't know I can move this. I can go H, E, B, A, C, F. Okay, so only this way. There is just one way of going. While in a graph, there can be these circles, these closed loops. So if I want to go from H to F, I could go that way. So I could go H, G, D, E, F, or I could go that way. So I have more than one ways, more than one paths to go from one node to the other. There can be these closed loops in graphs, which in trees they cannot be. And so also graphs have no root node, as I was saying. So there is no root. We can start our traversal or going through it from any root. And since there are no limits on the number of edges, so every node can be connected with all other nodes if we want, and there can be these loops created, we cannot use recursion in graphs, because recursion will end up, it can be the case that it can end up in an infinite loop, because I want to go to the children or the neighbors of this, and then I go this, and this, and then I get myself back, and then I'm on this circle. So if I try to go from H to visit everyone, then I can go back to H. And so recursion is a bit more tricky with graphs because I can have these closed loops. And also I need to keep track of the visited nodes. So when I start going from one node to the other, I will have some helper array or object or something to keep track of which nodes I have visited, so that when I get back to like one that I have already visited before, I know that, oops, stop here, don't go back again, so that I don't get myself mixed in this infinite loop. So these are the main difference with trees. There is no root and there can be loops. And so these loops, these circles can cause some issues that we have to take care of. And one of these is to keep track of the visited nodes. In trees, we did not, because we had the children, and then we know that if I go one level down, then for sure there is no visited node there, because there was just one way of going there. But maybe in graphs, I have arrived back to myself if I try to like go down, which is not, there is no direction. And in graphs, the depth first and breadth first are very similar, and none of the two is recursive. Remember, in trees, we had one of the two was recursive, was the depth first, I think it was recursive. Here, no, we don't have recursion, we don't use recursion, and the deep first uses a stack, and the breadth first uses a queue. We will see an example just right now. So the depth first, same as the trees, we try to visit the furthest node from the starting node. Remember, there is no root, so we just suppose one starting node, and we try to go as far from it as possible before we visit the rest. And this uses a stack. And the breadth first, we first visit the closest node. So first we visit the adjacent nodes, and then we go to the next. And this uses a queue. And in order to avoid these circular loops, we will be keeping somewhere all the visited nodes. And one way of doing it is having this object, the visited objects. Every time I visit a node, I add it to my visited object with 1 and the value of true, so that I know that I have visited the node 1. And so I could do it with other way. I don't really have to do it with an object. Maybe I could do it with an array as well. So to have an array of all the visited nodes, but we will be doing it like this with an object, because it's easier to directly see if I have visited node 5, for example, because if I check visited square brackets 5 or dot 5, if this is true, then it means that I have visited this. If not, if all the visited nodes are in the array, I would have to use some kind of find or includes item or something to see if this item is included in the array, and it will be more of array search traversal, so it will need more operations. So this way it's a bit more direct, even if an array maybe would be the first thing that would come as a solution to mind. But it can be done with both ways. We just suggest this one here. Okay, let's see how these traversals work. So the depth first. Remember that the depth first uses a stack, and we will see right now why it's using a stack. So let's say that we start from node 1 and assume that the nodes are ordered in a numerical order in these arrays. And so we start from node 1, and at the moment I'm starting from a node, I also add it to my visited object, so that I know that this node I have already visited. So the next step will be to add, it's a depth first, so it's a stack, and I add the 2 adjacent nodes of this node to the stack, 2 and 5. So remember that since it is a stack, I'm adding from one place, but then, so no, I'm adding and then I'm getting again from the top. So we are adding nodes one on top of the other, and then we are getting from the top. So these 5 will be the next one to consider. So when I added these 2 nodes on the stack, I also added it to my visited object, so that I know that these 2 are have already included in the stack, have already passed from the stack. So the next step will be to extract one node from the stack, and since it is a stack, I will get the last one, 5, and I will add its neighbors, its adjacent nodes to the stack. But 5 has 3 nodes, 1, 2, and 4, but 1 and 2, I will be checking each time if I have already visited these 2. So since 1 and 2 are in my visited object, I will not add them again in the stack, because if not, this is when I was going to add on a loop. If I was simply adding all the adjacent nodes of 5 to the stack, then that means that I will have to add again 1 and 2 and 4, and then 2 will be here 2 times, and then it will be messy. So I extract 5 and I add the nodes that are not yet visited to the stack. So in this case, 4. And so since it is a stack, the next node to take out, it's 4. And I'm adding again the nodes of 4, the adjacent nodes that have not been visited. So 6 and 3 will go to the stack, 3 and 6. Okay, and here is how I traverse it. So I went from 1 to 5 to 4, and then the next node to come out is 6. And then there are no more neighbors or adjacent nodes to add to my visited. They are all visited already, but there are still nodes on the stack. So I still keep extracting nodes from the stack and see, and then the last one, and the stack is empty. And so this is my result. The depth first traversal starting from 1 would be this: 1, 5, 4, 6, 3, 2. So I went all the way from 1 to 6 to the longest, the farthest node, and then I returned and added some of the missing nodes. Questions? It seems very easy on the drawings, right? Then when you have to implement it, it's a bit more complex. But so remember that we will need different things here. We will need a stack to be like our work in progress thing, how we are, where we are at this point, a visited object to keep all the nodes that we are going to be visiting, and then a result, which is where we are going to store in the order that we want the final result. And so let's see the breadth first as well. And this time we start with from node 5. So the breadth first uses a queue. So see here it says queue. That means that I'm going to be adding things, but then I'm going to be taking from the front of the queue. So 5, let's say we start from the 5, 5 is added to the queue, and it's also added to the visited object, the object that keeps the visited nodes. Okay, and so the 3, 1, 2, and 4, the 3 neighbors of 5 are going to enter the queue when I extract 5. So I take out 5 and I add 1, 2, and 4. But now, since it is a queue, the one that I'm going to be working with next is 1. Okay, 1, 2, and 4 was added to the queue, and so it was also added to the visited object, because I already consider that I mark them as visited. So I take, in the next step, I take 1 out of the queue, I take 1 out of the queue. And so I check the neighbors of 1 to see if I need to add them to the queue, 2 and 5, but 2 and 5 are already visited, so I don't add any more. I don't add them again because they are already visited. And so I take out the next one, 2. And in this case, I do have 1 node to add to the queue, that is the 3, that it was not visited before. And it's added to the queue on the back. But I still take from the front. So I take the 4th, that is the last of the adjacent nodes of 5. And I add the 4 neighbor. And so all nodes have been visited, and I just continue until my queue is empty. And this would be the breadth first way of traversing this graph, starting from 5. So 5, 1, 2, and 4, which is the 3 neighbors, and then 3, and then 6. It's not so easy to see as in trees. So in trees, they were more easy because there were no loops. And we had a very clear identification of the levels, and it was easier to see how it would go through. Here, we just need to focus on whether it is a queue or a stack. This will help us understand which one is the node to take out next.
For this one,
Mhm.
sorry. It looks like it's visiting the nodes in numerical order. Is that right? It's like 1, 2, 3, 4, 5, 6.
No, so this is
Based
not,
on where you started.
Yes, this is not, I think this is not correct here, at least on this. So, I mean, it should be 5,
Okay.
1 to
But then
4.
it was 1, 2, 4.
Yes. So this, the visited, yes, it just like it ordered them numerically, but at the end,
Yeah,
it's
'cause
not important because it's an object. And so in object, we
Yeah.
don't have any specific order. It's just as long as it is inside the object, then it's good enough.
Okay, I was just because like these are numbers, but it's possible to have like things here that aren't in order in some way, like colors or something.
Yes.
Then it wouldn't matter the order that they're
Yes, yes.
just that they're next to it.
Yes, it just matters if they are in the array, if they are adjacent or not. And so, as you say, it could be that it's not numbers. It could be something else. We could still use, if we had colors, we could still like try to order them alphabetically, but
Right.
yes, it's not important.
So it's possible that like the result order would be different than if you started with 5 instead of starting with 1, you started with 4.
Yes.
For example, then it
Yes,
would
it could
work
be
that way.
So when I add 5 to my queue, then I add the neighbors, the adjacent nodes. But if I don't add them 1 to 4 and I add them 4 to 1, then the first one to go out will be 4. And so the result will be 5, 4, 2, 1, maybe. So it will be a bit different. Yes, it would still be breadth first because I would still have visited the neighbors of 5 before moving, but could be different. I think in the examples that we are doing and the activity, we suppose that we assume that we order them numerically. Someone else also? Yes, had a question.
I'm a bit confused as to why, but maybe because initially my question was like in visited, it's the results says 5, 1, 2, 4, and visited doesn't list. It starts with 1.
Yes, I
rather.
think this,
But that's
this,
just,
let me see on the back. So it visited, it shows them in numerical order, but it shouldn't. So if I restart, so visited, it's first, it's 5, because it's the first one that you have visited. And then when you take out 5 and you put the neighbors 1, 2, and 4, 1, 2, and 4 should be after 5 on the visited. So it could be 5, 1, 2, 4, but here on the visited, at the moment that it adds something, it kind of numerically orders it.
okay.
But this order here, it's not important. It's how the object will be. The order that it's the result that we're searching is on the green here. So this is the breadth first thing. Yeah, so now it added 3, but it added it here in the middle because it automatically put those nodes in order on the visited part.
Okay.
I think there is also some, yes, so some
Um,
playground here. Yes, more questions.
Yeah, if you need to write the test for this, would you write all the possible answers? I mean, all the possible solutions of each thing?
So for the tests, I don't know if the tests are already written, I think. You will just assume numerical order so that you are following numerical order, and then the test should always be like one concrete thing because you are taking the orders out, the nodes out in numerical order. So you can just write the one that is with numerical order.
Okay, thank you.
It's not how it's working like in real life graphs. They don't need to follow a numerical order, but yes, for the tester, for making it more simple with implementation, we assume that we follow this. And so you see here also in the playground, always they are ordered like this. The adjacent nodes, they are put like this numerically, and then we also add them and remove them like this from the stack. So see here, you have a playground. If you want to try some more things, for example, starting node, let's say I put 6 as a starting node. And if I want to go breadth first, then I will be using a queue because it's breadth first. And so I start with 6 and I can check. If I take this out, then the next that will go to the queue is the adjacent node 4, and 4 will be marked as visited as well. And then 4 is taken out of the queue and its neighbors get in 3 and 5. And you see that I'm putting the neighbors like this, 3 and 5 and not 5 and 3. So I'm assuming I'm putting them in numerical order and marking them as well as visited. And then I take the first one on the queue, the front of the queue, that is 3, and I add the second, the 2 node, and I take out 5, 2 and 1, etc. So you can play a bit with this if you are if you have some question on how, like you want to review it. And I don't know if we have some. Do I have some other here? No. Some other link. Okay, so let's try to create from the activity. So I'm going to share the activity. If you have any questions, meanwhile, just tell me while I'm searching for the activity. Need to sign in. Okay. Going to share it on resources here. but we'll view it now. We'll see it now together. Okay, so here's the activity. Let me go. So we need to create the class and then create some of the methods included in a graph. Practice recursion, it says here, I'm not sure we're going to need recursion in graphs because we don't use recursion in graphs. Maybe it's a mistake from copying paste. There are a couple of links here that you can also check. Explanation of graphs and common methods for graphs. You can also check these for some additional information. And okay, let me clone this. No, let me see. I needed to, I should have gotten into this one. Okay. So the graph and the test here. And I need to see what was this one. Graphs and being installed first. So we have the constructor that, as we were saying, is this object with these with these nodes. Then a method for adding nodes to our graph, a method for creating an edge between two given vertices, two given nodes. So to connect basically node A with node B, to remove a connection and to remove a node. And then there are these two traverse depth first and depth first and breadth first. And here we need to specify starting node because it can be different. You can see there are some tests. Yes, there will be some tests with concrete starting node. And so in each case, we will be using a visited object where we're going to store, every time we visit a node, we're going to store it in here. And so for the depth first, we create a stack. And for the breadth first, we create a queue. In this case, as I was also mentioning with trees in a moment that we needed this, we did not need to create a very official stack or official queue class. We can just use an array and consider it to be a stack by just considering that it will be a last in, first out. So we will be just adding things on the end and also removing from the end. While on the queue, we just have, again, just an array, but we will be adding, pushing things and then shifting things from the front and shifting things from the front. So to make it look like a queue. Okay, but in fact, both of them are just arrays. And so let's start by trying to create. So this is the primary test case that we use. We have a graph like this with nodes A, B, C, D, and E connected like this. And so when we want to add a node of a specific value to this .nodes object, so that means that I need to create a key pair for this node to the object. So I need to take these .nodes and add a node with the value, that one that I'm passing. So let's imagine that I'm trying to create node A. So I'm going to add a node with a value A. It's the A that I'm passing here. So I'm going to create this key for my object. And at the beginning, I will just add an empty array to this because I don't have any neighbors. So I'm just adding this node without creating the connection with the edges. I will create the neighbors later. So why do I use this method? So this node is an object, right? So how do I add things to an object? So imagine this is an object and I want to add a new property. We had some objects before, and when we want to add a new property, we could use the dot notation or we could use the bracket notation. In this case, would these nodes dot value work like this? Is this the same? So could we use the dot notation? So imagine that value for our test case is A. I'm passing A because I want to create a node A with the value A, as the test says. So add node A.
If you put a dot notation, I think it wouldn't work because it would consider it as a variable instead of the parameter.
Exactly, this will not work because it will create on my object something called value. So it will actually take value as if it was a string, and it will create a value equals to an empty array. Well, maybe with no quotes, but or with quotes, it will take it as if it was a string, basically. So in this case, value, it's not something that I want to name a property. It's a variable that I'm going to be passing, and I want to replace it with the value that this property will have. So in this case, I need to use the bracket notation. Remember when we were discussing in objects the two ways, the dot and the bracket, sometimes they can be exchanged, so I can use the same thing for both. But when what I'm trying to access, it's not the name of the property itself, it's just a variable that holds the name of the property, then I do need to use the bracket notation. And so this would not work with the dot notation here. I would have to do it like this.
So then this new node would just be like floating by itself. It's not connected to the other ones yet. In this
So
case,
yes, in this case, it's not connected. Let me check. Annotate and H A to B. Should not override vertices previously added. Okay. So I don't see here my test run. So for some reason, my test is not running, but I will check. So this should add vertices to the graph and an empty array to hold edges. So this first test is passing. Should not override vertices previously added. So let's see what this is doing. So let me check here what this test is trying to do. So if graph nodes A, so A is one of my nodes, equals to B. Okay, so if this has like a B neighbor, graph at node 8. So, okay, if I'm trying to add the same node again, so what this test is doing is that it already creates a node A with a B as a neighbor. It's okay, it's the same as if it was empty also. It doesn't matter, the test will still not run. The thing is, what if I try to add the same node again? Okay, so I need to check before I try to add something that it's not already there as well, so that I don't create the same again. So if I had, let's say, if I had some neighbors created, so in fact, this is better. If I had a node already created with some neighbors and I try to create again a node, will it create a new node A with no neighbors, or it will keep the original node? That's what this test is saying. So that I'm not able to add the same node again. So before actually doing this, before adding any node, I need to check if this node already exists. So I need to check if this node's value. So if this exists, then I'm going to add. If it's not existing, sorry, if it's not existing, then I'm going to add this node. Because if it exists, I don't want to add more A nodes. So yes, in this, we just add the vertices. We don't add the neighbors. Then the second one would be to create the edges between two given vertices. So any idea how we would start here? We want to create the connection between two nodes, node A and node B.
Would you say the same as the other one, this dot nodes, and then in bracket you would put node A equals the node B, and then the same, but then switch node A and node B?
These nodes, node A, not, it's very, very close, as you say. So you need to create this connection and then switch B and A. But it's not going to be A equals to B, because what we want is to have an array. So maybe it has more neighbors, more adjacent nodes. So we actually want to push node B to the array here. So if we
node
just
A
make it, Mhm.
dot push, and then inside the parentheses node B.
Yes, so this would be this dot push node B. So I'm taking what was in here, that was an array, maybe empty, maybe not, because that doesn't mean that I ran this for the first time. There may be already some nodes in there, and I just push the new node in there. And the same thing I'm doing for node B, because I need to create the connection both ways. So for this node, I take, in fact, I don't really need this, I think, this node A. I just need to push to the array. I don't need to make this equal this. So I just need to go to the array of node A and push node B. And then I need to go to the array of node B and push node A. Because the push method, remember, it doesn't return anything. So if I made this equal what the push return, it would be undefined. The push already adds something to the array, and the job is done. It doesn't return anything. And here, this would almost have us done, just that we need to make sure before that both A and B exist. If not, it will be this, for example, if the B node is not existing, then this would be undefined, doesn't have anything to push to, because I have not created it before. So we either check, there is a node A, so we check if this node's node A exists, and if the other one also exists. So if both of them exist, then I just do the connection. And so if not, I need to create them first. And how I create them, I call the add node. So if they don't exist, then I need to create them. So then I need to create them first and then call them, and then use this connection. Okay, so in fact, I'm going to do the opposite. If they don't exist, or, so let me just write this differently. So I'm going to do it one by one. Let's say, first I check if this node is not existing, then this dot add node A. And then if the B doesn't exist, then I'm going to add the B. And then once both of them, I make sure that both of them are added, then I'm doing the connection between the two. So more questions here.
In the in the add edge method where it says node A and node B, you would input then like just the name of the node, like A or B or 1 or 2 or whatever it's called.
Yes. So yes, also on the test, I think we have it like this. It calls add edge on A and B. So it passes the two nodes as strings.
Okay, and you would just put A or B in there when you're calling it, or would it be a string with like the quotes around it?
When you call it, like you mean
Oh.
here, when you call the graph nodes A, it will be, when you want to replace it, it will be with the quotes.
Okay.
So yes, so A and B should add edge AB. And so that means that if I check graph nodes A, this should be equal to an array that has B inside. And in this case, it only has B because I know I'm just creating this for this test. So I don't need to check if there are any other, because the graph I take here, I get an empty graph. And then for this test, I just add two nodes. I know that I added A, I know that I added B, and I know that now I'm adding a connection between the two. So A will only have B. In the generic case, A can have more nodes, and I just need to check if B is included. And so I also check the opposite way. And in fact, I didn't have to do, again, the whole thing. I could just copy this expect here. So expect that A has B and expect that B has A. But anyway, the test is already created like this. And also check that we have this case here on the test. It should create vertices if they do not exist. So if I call add edge A, B, B, but without having called before add node and add node. So A and B, they did not exist when I call add edge in this test, in this case. So that means that the add edge itself has to take care of creating these vertices if they don't exist, as we are doing here. So it checks if this doesn't exist, then it does the add node. And then it does the connection. Okay, I'll let you start working with this, because like this you can get more questions, and I'm going to be here for so 1, 2. We have less people now, less and less. 1, 2, 3, 4, 5, 7. I'm going to create 3 breakout rooms, and I think you will be with some, maybe there's not 2, there are more. So that you can work a bit together. As I was saying, there is an extension in VS Code that is called Live Share that maybe you want to install and start the collaboration session. That means that the other can also edit. But if you want to make it quicker, then you can simply just share screen. And then at some point, one that has an idea then says, okay, let me start with this. And then the other gives ideas and helps and just watches at the moment, and then you reverse it.
Anna, sorry.
Yes.
I should go like in 5 minutes, so I think I will stop now because it makes no sense to do like 2 minutes of exercise.
Okay.
Then.
Okay,
Sorry.
okay. So on Friday, you have a session with, we have an invited speaker and a session with Joy. It will be around HTML, CSS, so that you remember a bit if you have not have any idea. And if not, you will see it on Friday, but also try to review it during the weekend because we will need a bit of basic HTML, CSS for the next week. Okay, so I'm going to open the rooms. You go, try to start working, and I'll join you for any questions.